Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we are here to put science in your brain. This has been a weird news week as the world turns. Things we expected, like the flight of the Mars helicopter Ingenuity, have been delayed to next week. And things like the flight of SN15, one of the Starship prototypes, have raced into next week. Meanwhile, we're seeing the standard mid-semester slowdown in new science, and I feel like everyone on our writing staff has a touch of spring fever. It's that week.
As much as we may be struggling to find news beyond, hey, all the flowers are in bloom, there are still a lot of new results, good and terrifying, coming out. As a resident of California, I want to remind everyone living and passing through the dry western states in the U.S. that we are facing the driest year for plants in, well, this is a new kind of bad. The moisture content in the plants and soil is so low, we are at risk of facing a fire season like no other. Thank you to my university for letting us know that. Everybody be careful. We here at the Daily Space want to see our humans unharmed, and we don't ever again want to sit vigil while waiting to see if observations will burn like we did last year. To quote Smokey the Bear, only you can prevent a forest fire.
As our technologies advance, teams are looking at how we can use artificial intelligence and robotics to solve complex problems that might otherwise endanger human lives, including firefighting. While I have to admit to being a bit disturbed by swarming cooperative robots on Earth, I'm intrigued by new research showing that nanosatellites can be programmed to work together. Specifically, the Skoltech Space Center's Nanosatellites Swarm project, that's not ominous, has enabled their tiny satellites to measure the Earth's geomagnetic field and pass that information along to other nanosats. Since the geomagnetic field can affect navigation, this information shared across a constellation of satellites allows the leading craft to warn their swarm mates so they can compensate in real time. According to a press release on the research, the new method can be used to build large constellations at a lower total cost by using less expensive sensors. This is super cool work. And while part of my brain is wondering, is this how we get Cylons? This feels like how we get Cylons. I have to admit, I'm in favor of lowering the cost of satellites we need for our modern lives.
I don't want Cylons. Folks, please be careful just how autonomous you make your machines. Please. It's days like today that are particularly good for imagining skipping off this planet to find a better one. And it appears that more and more places aren't just capable of having planets, but are capable of having habitable planets. New research published in Frontiers in Astronomy and Space Sciences with corresponding author Dr. Nikolaos Georgakakos describes 5 binary star systems capable of supporting habitable planets. Basically, if you want to watch 2 suns rise, these are the places you place a planet. According to Georgakakos, life is far most likely to evolve on planets located within their system's habitable zone, just like Earth. Here we investigate whether a habitable zone exists within 9 known systems with 2 or more stars orbited by giant planets. We show for the first time that Kepler 34, 35, 64, 413, and especially Kepler 38 are suitable for hosting Earth-like worlds with oceans. These worlds haven't been detected yet. Small worlds are hard to find, and larger orbits just add time to the problem. But these are places to look where we know planets in other orbits exist. So, yeah, Tatooine may totally be out there. Or at least it's double sunset over a desert, maybe something we can one day see.
Finding these kinds of challenging worlds and discovering many other kinds of dips and peaks in astronomy data is becoming more and more the purview of software instead of humans. Feed a machine learning algorithm a few tens of thousands of labeled galaxy images, and it will happily catalog another 27 million galaxies. Seriously, this is a thing that happened. And the work, led by Jesus Vega Ferrero and Helena Dominguez Sanchez, and published in monthly notices of the Royal Astronomical Society, is giving us an amazing census of the kinds of galaxies that have occupied the universe in the past 6 billion years. While classifying galaxies is time-consuming, this problem isn't actually hard for humans. Where machine learning algorithms are really excelling is in searching through massive data sets for extremely rare objects. Like playing a celestial game of Where's Waldo, it is often easy to look right at the kind of thing you're looking for and not see it among the stars. In a separate paper appearing in the Astrophysical Journal, a team led by Daniel Stern uses machine learning algorithms to pore through sky survey images, looking for distant quasars whose light has been affected by the gravity of an intervening galaxy. If the distant quasar and intervening galaxy are aligned just right, gravity can act like a funhouse mirror, creating multiple distorted images of that background quasar. This publication quadrupled the number of known systems where one quasar's light is distorted into 4 separate objects. There's nice symmetry there. These 4 times seen quasars can be used to study the expansion of the universe and other problems concerning the geometry of space and time. While this paper focuses on the discovery of these objects, we look forward to seeing all kinds of additional results that go from just finding these systems to, well, describing the universe. Finding things is hard. After the break, we'll be back to discuss finding life in seemingly impossible places inside the Earth. Stay tuned.
In order to understand where we should look for life on other worlds, we need to understand where life exists on Earth. Or maybe a better way to put that is we need to understand where life doesn't exist. The problem is no one knows where life can't exist. We keep looking and we keep finding life everywhere. Life is everywhere. A couple of weeks ago, in a back of the envelope calculation, Pamela assumed life on Earth is within 10 kilometers of the surface of the planet. While this felt like a huge expansion on what is realistic, this is apparently less and less so as researchers look deeper and deeper beneath the surface of the Earth and at the bottom of the seas. As we mentioned a few weeks ago, scientists working in Antarctica found life as advanced as sponges and related sea creatures beneath 3,000 feet of ice. Now, researchers looking 5,000 feet beneath the Earth in an old gold mine have discovered biofilms and other life living without light or oxygen. This former gold mine is part of the Sanford Underground Research Facility, SURF, located in Lead, South Dakota, and utilized the Deep Mine Microbial Observatory. In these environments, where even I never imagined life would be found, it turns out that different kinds of minerals are capable of providing the nutrients microbes need. According to project lead Caitlin Cesar, our results demonstrate the strong spatial dependence of biofilm colonization on minerals in rock surfaces. We think that this spatial dependence is due to microbes getting their energy from the minerals they colonize. These results show that biofilms can meaningfully contribute to the global nutrient cycles. Cesar goes on to add that these biofilms, and here I quote, have astrobiological implications as these findings provide insight into biomass distributions in a Mars analog system. While Cesar and her team explore beneath the Earth, researchers like Tanya Bosak are building on these results to search on the surface of Mars. The Perseverance rover carries 43 sample tubes, and it is hoped that sometime around 2031, a second mission will be able to pick up these samples and return them to Earth for analysis that we can't do with the instruments on Percy. The trick is trying to find the 43 rocks, most likely to tell the story of Mars's past, possible life, and today's still maybe possible life. As a field geologist, Bosak is using Percy to do the work she does with her hands and tools on Earth. According to Bosak, we work to understand the chemical conditions under which microbes make certain minerals or fossilize in certain ways, because that helps us understand and reconstruct what the environment was like. She goes on to explain regarding Jezero Crater that we have a habitable environment, we have a lake, we have all the sediments that are known to preserve the signs of life on Earth. Now, she just needs to find the rocks with those preserved signs, and we have to send a follow-up mission. And we have to wait more than a decade, but science is a long game, and we can't wait to learn what, in many years from now, we learn about Mars. While we wait, let's go to commercial. When we get back, we're going to talk volcano.
So we told you science is a long game, and you're just going to have to wait a little bit longer to get to those volcanoes. I'm going to talk first about an exploding star. The timescales over which our universe changes are often vast and beyond what humans have been around long enough to witness. Galaxy collisions, billions of years. Star formation, hundreds of thousands of years. Humans, we've just not been around that long. Sometimes, though, we get lucky. In 1054, a massive star in our galaxy exploded, forming a nebula and a pulsar. Today, we call this the Crab Nebula and the Crab Pulsar. And this system is one humans have gotten to watch across its entire evolution with increasing technological awesomeness. Today, this young system is giving us new insights into the energies pulsars are capable of throwing off. These Manhattan Island-sized stars spin at hundreds to thousands of cycles a second. And while most of the time these dense neutron stars give off a steady stream of radio pulses, sometimes, instead of steady pulses, they just throw out a giant radio pulse. In new research published in the journal Science, researchers led by Teruko Onato discuss how they looked at the Crab pulsar simultaneously in radio and X-ray to see if these periodic giant radio pulses are tied to activity in other wavelengths of light. And they are. The Crab Nebula is always giving off some X-rays, but they observed that during the short-lived giant radio pulses, these X-rays increase somewhat. While this increase somewhat is cool but not entirely exciting on its own, the combined result of massive increases in radio brightness and minor increases in X-ray mean that this dead star increases tens to hundreds of times in total emitted energy during these events. This is significantly more, tens to hundreds of times more energy than previously thought. These bursts are likely related to fast radio bursts that are seen coming from some not well-known source in galaxies too far away to resolve. If we can better understand how the Crab pulsar is misbehaving, maybe we can figure out what is misbehaving on the other side of the visible universe. When we learn more, we'll bring it to you here on the Daily Space. For now, we're going to go to break, and when we come back, we're actually going to talk about volcanoes. Last week, a volcano on the eastern Caribbean island of St. Vincent erupted after hours of spewing ash and steam. The volcano, La Soufriere, which means sulfur outlet in French, hasn't erupted since 1979. The first explosion shot a column of ash 10 kilometers into the sky, and according to reports from local authorities, was followed by 2 subsequent explosions. Heavy ashfall was reported in communities around the volcano, with lighter ashfall observed on the nearby islands of Barbados, St. Lucia, and Grenada. Despite the explosive ash, seismologists reported that this was what's called an efflusive eruption, meaning lava steadily flows out of the volcano onto the ground. As you probably know, this isn't the only volcano that is erupting right now. There is another, Figret as fall in Iceland. However, these eruptions are quite different. The Icelandic volcanoes have lava that is flowing out onto the ground from several openings and filling up the valley they're located in. So far, there haven't been large ash clouds like there have been with La Soufriere.
These are two different types of volcano. Iceland is over a hotspot and a mid-ocean ridge, so the magma welling up is hotter and less full of solid minerals. It flows faster. Meanwhile, La Soufriere is created in a subduction arc of volcanoes, similar to Japan and Alaska's Aleutian Islands. These volcanoes are created when plates are pushed downward toward the mantle, heating up and melting the rock. Add in some water to lower the melting point, and you have magma that is cooler, very viscous, and full of crystals. Think of honey that has hardened a little. You have to warm it up to get it flowing again. So while Icelandic volcanoes tend to be flowing and free, volcanic arc volcanoes have explosive eruptions as the partially solid magma backs up in the volcanic cones until the pressure behind the solid rock becomes high enough due to all the escaping gas in the rising magma. And boom, ash, rock, and lava all burst out, creating massive hazards for the surrounding communities. And that is why tourists are flocking to watch lava flow in Iceland and being evacuated on St. Vincent. You can roast a hot dog over a gentle lava flow. Do not try this at home, despite what you may see on YouTube, but get far away from a mountain that's due to explode.
We hope that the communities on St. Vincent remain safe and receive the assistance they need to survive this latest eruption. This has been The Daily Space. Join us tomorrow for a double dose of science where we record 2 shows back to back.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.